Hello, everybody. Today, we are going to be going over Unit 4 of Calculus 1, which is considered by most one of the harder ones because it's all about contextual applications of the derivatives that we've learned in earlier units. So, we're going to be going over things such as related rates, and we're going to be going over velocity, acceleration, and position functions. So, the fundamentals of this unit are that the position of an object given by, we'll use white, given by x of t, this represents the position. Sometimes you'll see it written as s of t, but that can get confused with different things. So most use x of t. This is going to equal, let's say, 3t minus 2. So this is essentially saying after t seconds or t minutes or whatever units that we are trying to use, after that many minutes or seconds, this is where the position of the object is going to be. This is how far it would have traveled, essentially. So the idea is that when we take the derivative x prime of t, this is going to equal v of t, otherwise known as the velocity function. So our velocity function is just the derivative of this function here. So the derivative of this is just 3. So it's essentially saying that the position is changing by 3 meters per second. And we'll just use seconds as our time. It's changing by 3 meters per second is the position. So at any given time, the velocity is going to stay constant. Now, what happens if we take the derivative of our velocity, v prime of t? This is going to be a of t, otherwise known as our acceleration. So this is how fast the velocity is changing at any given time. So in this instance, a of t is equal to, well, our velocity here is 3, and the derivative of 3 is 0. So in this case, our acceleration is 0. Our velocity is always 3. So that's what shows us what our velocity, acceleration, and position is at any given time. You can go further. There is such thing. You can take a derivative as many times as you want to check different metrics. However, for this video, and for simplicity reasons, we're only going to work with velocity, acceleration, and position. Let's move on to an example, not even quite related to speed, but related to volume and temperature. So the temperature in Celsius of a cup after t minutes of being poured is given by x of t equals 75 plus 30 e to the negative 0.1 t. How fast is the temperature changing 6 minutes after the coffee was poured? Okay, so the idea of this problem is that we have our function x of t, 75 plus 30 e to the negative 0.1 t. So the idea is that if we take the derivative with respect to time on both sides, then we're going to find how fast the temperature is changing. In this case, Celsius per minute. In this case, we're going to use Celsius per minute. So for this specific problem, Our constant is just going to cancel out, so we're just going to have 0. Let's actually label this as not necessarily our velocity, but let's say our Celsius in terms of time. This is going to be equal to our constant, which is 0, plus, remember when we're deriving e raised to some power, it is equal to, we keep the e to the negative 0.1 t, and then we multiply by the derivative of the top power. So the derivative of the top power is just negative 0.1. So this is just, in the end, this will be minus 3 e to the negative 0.1 t. Let me clean this up a little bit. Okay, so we want to find how fast the temperature is changing after 6 minutes. 6 minutes after the coffee was poured. So the idea is that we just plug in 6 because that is how many minutes have elapsed since the coffee was poured. So we're just going to plug in negative 3 e to the negative 0.1 times 6 is 0.6. So that means if you plug this into a calculator, this is approximately, of course, 1.646 degrees Celsius per minute. Let me move this answer a little bit more centrally. Okay, so this is in fact the answer to this problem. 1.646, or sorry, negative, forgot the negative. Can't forget the negative. Negative 1.646 degrees Celsius per minute. So what this means is that after 6 minutes, the temperature is decreasing by 1.646 degrees Celsius every minute from now on. From then on, after 6 minutes. And it makes sense because the coffee was poured at some initial temperature, and since the coffee is likely in a room with a colder temperature than itself, because coffee is usually pretty hot, the temperature of it is going to decrease. And in this case, it's going to decrease exponentially. So we could find the acceleration on how fast it's going to change. So that is the main idea with this concept, is that you're trying to find rates at which things change. Let's go to another problem. The area of a puddle of water is increasing by 0.16 square inches per second. Find the rate of change of the radius when the radius is 20 inches. Okay. Let's first digest this problem. We have the area of a puddle of water, which we're going to assume is a circle, is increasing by 0.16 pi square inches per second. Find the rate of change of the radius r, when the radius is 20 inches. So we need to find it when r equals 20, essentially. So the idea is that our change in area, which is we're going to label as dA, with respect to time, the derivative of area with respect to time, essentially the change in area over time, is going to be, it's going to be equal to firstly, actually, we know that the area is going to equal pi r squared. Okay. The area is going to equal pi r squared. And if we want to find the change with respect to time of these, we want to find how fast the radius is changing. We take d, dt on both sides. So the idea is that we use our implicit differentiation to find out that the change in area over time is equal to 2 pi r times dr dt. dr dt is what we want to find because that is the change in radius over time, and that's what the problem is asking of us. Okay, so all we have to do is plug in r equals 20 as shown in the problem. So we have 40 pi times dr dt is equal to dAdt. dAdt, we can just replace that with 0.016 because that is the change, or 0.16 pi, because that is the change of the area over time, and we already got that in our problem. So now we're just going to divide, and we're going to get the change of the radius over time is equal to 0.004 inches per second. So this is the change in radius over time at when the radius is 20 inches. So that is how you use related rates and implicit differentiation to have contextual applications of derivatives in calculus. This is one of the harder units, but I hope I made it a little more digestible in the way that I explain things. Just to recap, when we found the change in temperature of coffee, we took our position, or essentially our, in this case, our temperature modeled by x of t, and we took the derivative with respect to time of the function, and then we were able to find out how much the temperature changed per minute at 6 minutes. And for our second example, we found a way to relate the radius of a circle to the area, which is pi r squared. Area is equal to pi r squared. And when we take the derivative on both sides, we are essentially getting the change in area over time is equal to 2 pi r times the radius changing over time. So we just substituted everything in that we got in the problem, and then we solved for the rate change in radius over time. And in this case, that is 0.04 inches per second. Anyway, I hope you liked this video, and I'll really appreciate it if you subscribe and like for more videos. I'll be trying to upload more daily, more often. Anyways, goodbye.